So I wanted to go over homework 6 a little bit. One thing in this course, which is frustrating, I think, for a lot of students, is that we're not going to spend time going through the calculations by hand. We just really want to get our answers and interpret those results. You can take Stat 243, 244, and we would go into these functions a lot more in depth. So this is really just a survey methods course on how to interpret those statistics. So don't feel like you have to do all these sums of squares by hand. You won't have enough time on an exam to do it by hand. So here's an ANOVA table. An ANOVA is testing 3 or more averages. Actually, ANOVA can be used for many things. You'll see later it's used in regression. It's used in other types of statistical problems. But right now we're looking at 3 or more means. And we have a blank table here. And we have a total, and the totals, these sum of squares in this column up in here, would have to equal 288. So I'm going to select this blank cell here, and I know that if something plus 168 has to equal 288, I can go backwards. I can take the total of 288 minus my 168, and I'm left with 120. Same thing with my degrees of freedom. They have to add up to 29. So if I take my 29 and I subtract 5 from it, I have 24. Sum of squares, mean sum of squares. These are all sums of squares, but the mean sum of squares, also called the MS, sometimes you'll just see MS in the header on this column, is the sum of squares divided by their corresponding degrees of freedom. 120 divided by 5 is equal to 24. 168 divided by 24 equals 7. Now, real life data, usually these are not going to come out to be integers, even these sums of squares. Degrees of freedom will be integers, but not the sum of squares. So make sure you go out enough decimal places so that by the end your test statistic is accurate out to 3 decimal places. To get this F value here, we're going to take 24 divided by 7, and we get 3.429 out to 3 decimal places. I want to check my answer. Great, works good. There are how many population means being tested? Well, that comes into here between groups, degrees of freedom. The formula for that is k minus 1. K is the number of groups. So I would have 6 groups. Let me check my answer. Looks good. What are the hypotheses for this test? Well, always in the null, we're going to have equal means. So all the means are equal comes into play in part C or D. And it's not that none of the means are equal, it's just that it means one or more of the means are not equal to one another. So the difference in part C and D comes in here. None of the means are equal. Well, we could have 2 means equal and 2 means that are not equal. We could have 1 mean that's not equal to the other 4 or 5 in the group. So we're going to want to choose C. Not all the means are equal. Now, if you were actually writing this out, you'll see a lot of times that in the null, you'll write it as mu1 equals mu2 equals mu3 equals mu4 equals mu5 equals mu6. That all 6 means are equal to one another. And then the alternative hypothesis will say at least 1 mean is different. We write that as a sentence because we have, it's not just that all 6 means are unequal, we have any one of the 6 values are unequal to one another. So let me check my answer. Looks good. All right. Determine the critical value. This is what we're going to want to use Excel for. We're going to go up here. Here's our 5 and 24 degrees of freedom. This is always a right-tailed test. So I'm going to open up Excel. So our F distribution is built into Excel. I just have to type in equals F, and there's all these different things to choose from. F.dist and F.dist RT right tail would be to find a probability. So if you were wanting to find a p-value, for instance, you would use those two. We're going to find the critical value, and we're going to use the inverse function. And inverse left-tailed is the INV, and inverse RT is the right tail. And the ANOVA test is always a right-tailed test. So we're going to want this one, inverse right tail. Probability is your alpha, and that was given as alpha equals 0.05 in the problem. And then our degrees of freedom, we had 5. Oh, and let me go back. I actually have forgotten that we have 24 degrees of freedom for the other group. Oops, I forgot my comma, so I'm going to backtrack here. 524 in my parenthesis, hit enter. So 2.621 out to 3 decimal places. Again, if you're having a hard time with rounding, you can always decrease your decimal places and you can get the rounded value, 2.621. So now I can go back to my homework here and I can put in here 2.621. Check my answer. Looks good. All right. State the conclusion for alpha equals 0.05. Since the f-test statistic is, well, if we're looking at this, the right tail is what we're working with, and our test statistic is 3.429. It's bigger than our critical value, so it's out in the tail in the shaded area, so it's going to say f-test statistic is greater than the critical score. And when your test statistic is greater than the critical value on a right-tailed test, we would reject the null hypothesis, and we're going to conclude that at least one of the population's mean is different. All right, check our answer. Here we go. All right, next question. Here we have some data, and we want the sum of squares for total. Please do not do this by hand. There's absolutely no need for it when you're going through. So we're going to want to actually type this data into Microsoft Excel. And we're going to keep in mind that alpha equals 0.10, and we have 3 groups, sample 1, 2, and 3. So let me pause for a second, and I'm going to type that data into Microsoft Excel. All right, here we are with the 3 data groups typed in. I just typed those in myself. It's pretty quick. Sometimes you'll be able to copy and paste the tables right from MyMathLab. Make sure you're consistent on your headers. You have a label in each of your columns because we're going to have a box that has labels later on. You don't have to have labels, but it's helpful. I'm going to go up into the top here to my Data tab, and I'm going to choose the Data Analysis tool. Again, if you're working on a Mac and you don't have this, you can use the XL Miner tool in Google Sheets, which will do it as well. But you're going to go to the Data Analysis tool. It's alphabetical, and the ANOVAs are up on the top. We're right now just working with the single factor ANOVA. In fact, in this class, we're never going to be doing the with and without replication. Those are more complicated design. We go through those in 244, Stat 244 and Stat 366 if you're ever interested. We're going to say OK. Input range, we're going to highlight all of the data, including the labels. It's okay to have these blanks. You do not want those zeros. This would actually be data points of 0 and would change your averages. We're going to select the labels in first row box. Now, again, be very careful of this. If I did not highlight the label and I checked this box, 7, 2, and 3 would have been the label, and I would be 1 short of all of my values. And now our alpha was 0.10 for our problem, so we're going to want to change that. Again, if you were going back to our data here, you have here up in the value alpha equals 0.10. Output range, you can select a new worksheet. That's probably the easiest. If you want to do output range in the same sheet that your data is in, you would select this circle, and then be careful because right here it's highlighted on the input data. So you want to select inside the box output range. It's just one cell where you want the table to start. So I'm going to start it on E1. So I could type in E1. I just use my mouse and clicked on cell E1, clicked OK, and here is my output. And I have my sum of squares here, and you can double click here to get the length, just so you can read each group. Our question was asking for sum of squares total. SS stands for sum of squares. Here's our total, so 44.1. Go back to my homework assignment, type in my 44.1. All right, that checks out. Sum of squares between groups is the next piece in there. So if I go back to Excel, my sum of square between group was 14.1. Alright, that checks out. Sum of squares within groups, here's my within groups, that would be 30. Okay, Now we have the table, and they want us to replicate those values in the table itself. So I'm just taking each one of these numbers in here and putting those values. Just be careful that degrees of freedom, mean square, and F are in the right order. So we have our 14.1, that was 30, total was 44.1, degrees of freedom, we had 2, go back here real quick for my degrees of freedom, 7 and 9. Oops. And then our mean sum of squares, we have 7.05, and 3 decimal places for the things that go out farther. So for our mean square within groups, we'd have 4.286. That 5 gets rounded because of the 7. And our test statistic, 1.645, that was this F here. Notice it also gives us a p-value and a critical value, which is nice. When you have the raw data, you can get Excel to have all of that for you. Alright, check my answer. It comes out good. Part C, let mu1, mu2, and mu3 be the population means of samples 1, 2, and 3 respectively. What are the correct hypotheses for a one-way ANOVA test? Right away, you'll never want equality in the alternative hypothesis. So C definitely cannot be your answer. And then on the reverse of that, you never want the unequal signs in the null hypothesis, so part B is out altogether. That leaves A and D, and A is close. The null hypothesis is correct. Mu1 equals mu2 equals mu3, but we could have a possibility, say mu1 equals mu2, but they do not equal mu3, or maybe mu3 and mu2 are equal but not mu1. There's all these different ways that they could be unequal, so instead of saying they're all unequal, we say not all the means are equal to one another. So part D. What is the critical value? And again, if you have raw data, we could have done the f.inverse function in Excel, but part of our Excel output is getting, it gives the critical value right here for us. So 3.257 would be our critical value. And check my answer. Looks good. What is the correct conclusion? We're comparing this 1.645 here to the 3.257. The F statistic does not fall in the rejection region. And so we would have do not reject the null. The data do not provide sufficient evidence to conclude that the population means are not all the same. Alright, I've skipped ahead to problem 5. The other problems are pretty similar to what we've already done. This one has what we call multiple comparisons. So when you reject the null hypothesis, it says that there's a difference in the means, but it doesn't tell you exactly where those differences are. So you don't do the multiple comparison unless you reject the null in the ANOVA test. And then there's a different type of test that we're going to use if we reject H0. So we first have to go through the ANOVA, and same arguments as before, but we're going to want our hypotheses that the means are equal and not all the means are equal as the alternative. And then now we have data up in this icon. I can click on the icon, and I could copy it by this little tiny icon over to the side, click to copy table, and I'm going to, you can do it a couple different ways. I can open in StatCrunch, or I can open in Excel. So if I open in Excel, it has downloaded a file for me. Here's my data set in Excel that we just opened, and it has just labels A, B, and C. I'm going to go to my Data tab, Data Analysis, Single Factor ANOVA, and then my input range, I'm going to highlight my values. Labels were in the first row, and I can't remember alpha. Let me go back to the problem. Let's see, alpha was 0.05. And for my output range, and I'm going to go ahead and do the same spot here. There's my output. And I'm going to copy these numbers back to my table. So we have 16 and 671.3. Our total was 687.3. And then our degrees of freedom, 2, 21, and 23. Our mean squares, I had 8 and 31.9. Six, 7. Out to 2 decimal places they want this time. They keep changing that on us, don't they? Alright, 2 decimal places. And then our F is 0.25. Okay. Our p-value, that's also in our Excel output. That's right here. 0.7809. How many decimal places do they want? Round to 3, so 0.781. Now that's a very large p-value. And anytime your p-value is greater than alpha, which 78% is definitely bigger than 5%, we're going to do not reject the null. Include that the average weight is not different for these delivery companies. So when you have this case, which means are different, we would say none of the companies are different. So we won't have to do a comparison test.